My name is Mark Tyrell. I am the host, the moderator for PyData Global for this session. I'd like to introduce you to Jacob Tomlinson, who will be conducting the session or the workshop today on GPU development within Python 101. Jacob is a senior Python software engineer at NVIDIA, and I'm sure you can pick it up from there, Jacob, and probably introduce yourself better than I can. So I'll hand it over to you now.
Sure. Thanks, Mark. Hi, everybody. I'm Jacob. I'm a software engineer at NVIDIA. I mainly work on a suite of open source Python libraries called Rapids, which are like GPU accelerated kind of re-implementations of the core PyData stack. So NumPy, Pandas, scikit-learn, we kind of re-implemented as like CuPy, cuDF, QML, and a whole bunch of other tools within that suite, right? So I work a bunch on that. I'm also a Dask maintainer. That's kind of like my main contribution to Rapids, actually, because we use Dask within Rapids to scale out to multi-GPU workloads. So I do a bunch of work on Dask kind of day to day. But the idea of this workshop really is I joined NVIDIA like 2 years ago. I was already a Dask maintainer. I was already working in the like Python, PyData space. And I kind of came into NVIDIA fresh, not really knowing a huge amount about GPUs. I knew about distributed computing, and that was kind of what I was bringing to the table. So in the last couple of years that I've been in the organization, I've been slowly kind of skilling up on GPU development. And so it's not like a huge part of my workload, really. I'm more focused on the distributed side of things. But as I've kind of gained knowledge of how to write GPU code and how to interact with GPUs, I wanted to put together a tutorial that's maybe like an insider novice's perspective, right? I work at NVIDIA, but I'm not like a full-on GPU developer. So maybe I can kind of share what I've learned and give you hopefully like a gentle introduction to GPU development in Python. So let me share my screen, and we're going to work through a bunch of material basically on Binder, but on like a specific binder that I've set up. So if I jump over to here, you should be able to see that I'm already logged in. If you can't see what I'm doing, please shout or prod the host. But if you, I've got a bit.ly URL down in the bottom corner. So this isn't regular Binder. This is a binder that I've thrown up for this session. So this bit.ly URL down here, which should take you to this Binder page. Now this is like Binder's great. It's an open source, free platform for running sets of notebooks in like an interactive environment. But the default Binder environment doesn't have any GPUs, and since we're going to be doing some GPU development, we need some GPUs. So I've thrown up my own stack of Binder. It's just running on some random like Google Cloud machines at the moment. You should be able to come through. That link should kind of populate you through all the way through to this page. But the actual material is on my GitHub. So if you head to GitHub, it's just under Jacob Tomlinson /GPU Python tutorial. This is the material we're going to be running through today. So kind of if you can all start going and getting through to this point, it might take a little while to get in. I've tried to like preheat the cluster. I think there's like 1,000, there's about 100 seats available. So as long as we don't go over maybe 100 participants in this tutorial, we should be fine. If you have any trouble with this, kind of shout in the chat. I can kind of point you to other places, but really, this is going to be the best way to run through this material. Every participant, when you come through and into this Jupyter environment, you'll get a dedicated P100 instance, P100 GPU, sorry, that you can make use of. So let me kind of ramble my way through the intro, and hopefully you'll all kind of get yourself set up to this point. Don't worry too much about the things I've got down the side here. We'll kind of get to all of that later. But yeah, as I said, I've kind of been learning this, GPU development over the last couple of years. And I think the most surprising thing to me is I didn't have to learn any C++. I'm not really, the only C++ I ever really write is for like Arduino microcontroller stuff in my free time. I don't really have to write C++ as part of my work. And I haven't had to write any C++ as part of this tutorial. Everything here is in pure Python using some like fantastic open source libraries that we already have within our community. So we're going to work through like a bunch of notebooks. If I just pop open the file browser, I'll keep that closed to try and keep the clutter off. But you can see we've got a whole bunch of things that we're going to run through here. Let me drag that over. Oh well. We're mostly going to focus on number for the first half of this, and we'll get into what number is in a minute. But we're going to kind of go through GPU, what the programming model is like. It's like a completely different paradigm to writing for the CPU. We're going to start writing a bit of like hello world code and digging a little bit into how we manage memory and how things are shared between the CPU and the GPU. Then once we've gone through all of that, which is like, reasonably intro hello world type stuff, we'll dig a bit into figuring out what's going on in the GPU. We'll have a look at, and then we'll look at some more higher abstracted libraries. So we'll have a look at CuPy, we'll have a look at cuDF, which is like a data frame library. And we'll have a little look at QML at the end, which is like a machine learning library. And we'll do a little bit of like, we'll train a model and do a little bit of machine learning at the end, time permitting. I've run this before. It took kind of just over the 90 minutes. So I'm going to try and keep to time, and we should be able to get through all of this material. A couple of these notebooks are labs. So I'll be quiet for 5 or 10 minutes, let you have a work through those as we go. I think there's a couple of them in there. And then we'll go through the answers of those together to try and give you an opportunity to explore that. So let's kind of jump straight into this first notebook and figure out where we're going. I just cleared all my kernels. So let me just shut them all down again. Cleared all my notebook outputs to neaten this up. But let's jump into here. And then I'm just going to make sure I've got a kernel on this one. I don't know if I need it, but anyway. So CPUs and GPUs are two different types of processor that you have in your computer, right? And it's, I've always thought of, your CPU is the brain of your machine, and it is handling everything that's going on. And traditionally, the GPU is there for doing graphics acceleration, right? It's there to calculate what pixels should be rendered onto the screen, primarily in video games, but also used a bunch in movies and video editing and photography and all that kind of stuff. Now, over the last, 10 years or so, GPUs are becoming more and more general purpose in their use, and you can run kind of any code now on that processor. And that processor is architected in a completely different way to a CPU. So if you look at this big diagram here that I grabbed off the NVIDIA documentation site, you can see the CPU on the left has generally got a small number of cores, right? This is showing a 4-core processor. Modern processors maybe go up to 8 cores that you might find in like a laptop. Sometimes those cores can be shared between 2 different threads, so you get hyper-threading, and they kind of show up as more. In high-end servers, you may get more threads than that and cores, but you tend to have like a small number of very powerful cores that are all kind of controlled independently. The machine can be running different things together, but say you've got a 4-core processor, you can run 4 processes at a time on that chip, and the operating system will be sharing those cores between all the applications running on your machine. You've got like a whole bunch of caches, and then you have some RAM in your machine, and that is like your main memory. Your applications, your data gets loaded into that RAM. Now, GPU is different in that it's got many, many, many cores. I can't remember off the top of my head for the P100s we've got here, but it's going to be a few thousand cores in the GPU. And all of these cores have a lot more like shared resources. So they have shared control registers, they have shared caches, they have shared RAM, they have smaller amounts of cache. And that's because we work with all of these cores as if they're one thing. So although we have maybe 1,000 cores in our GPU, we're still going to pass a function to it, and that same function is just going to get called on all of the cores in parallel. And so you have to think about writing your code in a way that what happens if I execute this many, many times at the same time, compared to in traditional processing, where you might think about, well, I've got a single threaded application, I might fork my process and do a couple of things on a couple of different threads. If you're kind of getting fancy with it, but the GPU is a completely different paradigm. So there's a great video from Mythbusters that you can find on the NVIDIA YouTube channel. I recommend you go and watch that. What I'm going to do is I'm going to press play, but you won't be able to hear it, but I'll just kind of talk you through what they're saying in the video here, right? So the first thing they've got this little robot that is a CPU, and it's going to paint a picture using paintballs. And so it is going to fire one paintball at a time, and it's going to paint a picture on a piece of paper. This is kind of what a CPU is doing, right? It's doing one operation at a time. It's doing it pretty quickly, and it's pretty versatile, right? But you can get it to do all the things you want. You can take that paintball gun off and put something else on the end of it, and now it's kind of a more robust machine. Whereas the GPU is kind of more custom designed for doing one thing and doing it well. And so they've got this second machine here, which has got thousands of paintball tubes in there, and they're all preloaded with a paintball, and they're all connected to these big gas canisters. And when they set this machine off, It's going to go off and all of those tubes are going to shoot paintballs out all at the same time. They're doing exactly the same thing, but they've got a different configuration, right? They've each got a different color in. And so they just paint this picture in one big go. And so this is more akin to what a GPU is doing, right? It's doing the same operation with slight modifications in one go. And so you can kind of batch through your work. Now, apologies if that video didn't come across in the screen share so well, but please do, click the link, watch the video. It's really good. So thinking about the fact that we've got these two separate devices, whenever we write Python code, traditionally, it's going to run on the CPU, right? I can open up a text editor. I can, write print hello world, and I can run that Python script. I can just write Python my script, and it will run. And I will know that that will run on the CPU. And so how do we run something on the GPU? We have to specifically ask the CPU to tell the GPU to do something. It's like a secondary device that we have to explicitly interact with. And a great way I found to think about this for myself is that think about trying to run code on a different machine, right? Instead of running this Python script on my laptop, what if I want to run this Python script on a server that I've got, or some machine in the cloud or a supercomputer or something, right? Well, the first thing I'm going to have to do is I'm going to have to connect to that other machine. I'm going to have to log into that other machine somehow. Maybe I'd use SSH. Maybe I'm going to use VNC or remote desktop to get like a graphical view into that machine. But I'm going to need to connect to that machine, log in, and then I'm going to need to copy my script onto that machine. And so I might use SCP, I might use FTP. There's like a myriad of different ways that you can copy a file from one machine to another, but I'm going to have to copy my code from my laptop onto the server. And then over my remote connection, I'm going to have to ask it to execute that script. And I'm going to write, Python my script, but in like a bash prompt on that machine. And so it's running stuff on a GPU is a similar thing, in that it's like a separate device, and you've got to think of it as a separate device. But instead of using SSH or remote desktop or anything like that, we're going to use something called CUDA, right? This is NVIDIA's way of interacting with NVIDIA GPUs, and it's got all the same kind of utilities, right? You've got functions that you can call for connecting to the device. You've got functions you can call to move code onto the device. You've got functions you can call to move memory back and forth and data around. And then you've got functions that you can call that will execute those functions on the GPU. And so, CUDA allows us to interact with the GPU in the same way you would interact with a separate machine. Now, CUDA historically has been written in C++. It's a language extension to C++. But at the beginning of this, I said, we're not going to see any C++, and don't worry, we're not going to dig into any C++. CUDA's kind of been growing recently. There is actually kind of native support in Python coming. But the main way that we tend to interact with CUDA through Python at the moment is with a library called Number. Now, Number is a really awesome library just for speeding up your Python code. And if you've not seen it before, I recommend you go and check it out. Through this tutorial, we're going to be using the CUDA subpackage of Number. But what Number does is it looks at your code, and you can use like a decorator in Number to decorate a function. And when you call that function, Number will inspect the code. It will use LLVM to kind of compile that Python into something that's a lower level. So this is, it's a different way of executing Python code. The Number supports like a subset of the Python language. And this works on CPUs really well, right? You can decorate functions with Number JIT, and it will compile that function at runtime and execute it, and you get some performance boost. But Number has also got a CUDA extension, which means that you write a function in Python, you decorate it with the Number CUDA decorator, and it will compile it using the NVIDIA compiler into something that is like a CUDA compatible binary. And it also handles binding to CUDA to actually execute that function. Now, that's kind of gone a little deeper in the explanation than we're really going to need to worry about as we go through. But just, suffice to say, we're going to be using Number to run our Python code on our GPU. Now, we're going to dig into this low level for a little while, but then towards the end of the tutorial, we're going to come up to some higher level libraries where we don't have to worry so much about code getting compiled across and moved around. And we can interact with arrays and data frames and things in a way that maybe feels familiar if you've used NumPy or Pandas. And those are through the Rapids libraries, so CuPy, QDF, QML, etc. We'll kind of touch on that a little bit more towards the end. So let me move on to the next notebook. I'm just going to stop the kernel on that one just to keep my session as clean as I can. So number, this first notebook, we're going to dig into what the execution model is like on a GPU with number. So yeah, just trying to think about what I've gone through and what I've not gone through. So number handles converting your code and moving your memory back and forth. And so the first thing we need to worry about is writing some code to run on the GPU. When we talk about code that's going to run on the GPU, we talk about things called kernels. Now, this isn't the same as like the Linux kernel or anything like that. A kernel is like a piece of code, a piece of compiled code that is going to execute on the GPU. But that's a slightly scary word and it's an unusual word. So let's just think of it as a function. Kernels are just functions, but they have two very different features that make them slightly different from a function. So the first thing is that a kernel can't return. We can't return anything from a function. And that's because we're going to call this kernel thousands of times on our GPU. We don't want every single one of those trying to return something and shove data back somewhere to the CPU, to some other thread. But returns don't make so much sense. So what we do when we're writing for the GPU is we just modify memory. Right? We move some data into memory. Sometimes that's just like a big empty block of space that we're going to write to. And then as we run our kernels, or our kernel is run many times, each one of those executions of this function is going to modify some piece of memory. And then once they've all finished, we can go and retrieve that memory and grab our result. So in addition to not being able to return and having to modify memory, the other thing we have to do is we have to specify something called the thread hierarchy. And this is this kind of size and shape of the execution of this function. And this is like a slightly abstract thing, and it's a bit weird to think about when you first start thinking about it. This is one of the big hurdles I had to jump over mentally when I was getting into GPU development. But you basically have to say, I have this function, I want it to be called 12,000 times on the GPU. And you have to make that decision. How many times will this be called? And that kind of the number of times it can be called depends on your code, depends on what you're writing. Quite often this kind of stuff is used for image processing, and we're going to do some image processing a bit later in this tutorial. So say I have an image that's like 100 by 100 pixels. That means I need to, if I want to do some operation on that image and modify each pixel, I need my function, my kernel, to be run 100 by 100 times. 10,000 times. So I can kind of work out based on my problem how many times I'm going to need to execute this. But we can't just say, please run my function 100,000 times, 10,000 times. We have to specify it in a way that the GPU is expecting. And this is because GPUs do have a finite number of cores. So you can't just say do it 2 million times and it'd be able to do that all at the same time, because there might be only 1,000 processing cores in there. So it's going to need to batch those executions. You can say to it, call it 2 million times, but it will do it in chunks. And we tend to call those chunks blocks. So what we do is we specify how many threads we want in each block, and then how many blocks we want in each grid. Right? When we call a function, we call it a grid. So we kind of got some diagrams here that I've again pulled from the NVIDIA documentation, and you can see each block here at the bottom of this diagram. I don't know if you can see my pointer, but the kind of the yellowy box with the orange boxes in. This is a block which contains threads, and you have to specify how many threads go in your block. This is kind of the smallest unit of measure that we can work with. Now, there are some advantages to having threads in the same block. They've got like different levels of cache that they can access. And this does matter when you really get into the weeds, but I'm not going to worry too much about that. Let's just think of this as we need to specify how many threads are in a block. And then we need to specify how many blocks we want to call all together. So say we set our blocks, the number of threads to 512, just because that's a nice round binary number. And say we want to call our function 10,000 times, we need to work out, well, we're going to do it in blocks of 512. So how many of those blocks do I need to cover, the number of times I want to call this? So once we've kind of decided how we're going to chunk up our executions, those blocks get passed to the GPU, and the GPU will hand those to kind of the smaller units of compute on the GPU, which are called streaming multiprocessors, but that's not worried too deeply about that. All that we need to take away from here really is that we're going to write some functions. Those functions are going to modify memory instead of returning, and we need to tell it how many times to run those. Now we have some rules of thumb for working out some of these numbers, because we're going to have to work these out. The number of threads per block should be around multiple of 32. This is just because GPUs have some kind of small unit of measure called a warp, which again, don't worry too much, but we just tend to say rule of thumb, don't make them odd numbers. They need to be a multiple of 32. A good place to start generally is like 128, 256, 512, maybe 1024 if you've got like a modern GPU. And so we're just kind of go with these defaults. These defaults are written in the number documentation. They're written in the NVIDIA documentation. Let's just assume they're good and carry on. So what I'm going to do quickly, I'm just going to pause for a second and have a look at my Kubernetes cluster and make sure folks are managing to kind of log in and get set up on Binder. I don't know if you can see my screen, but it doesn't matter too much. But yes, okay, it looks like a bunch of people are logged in. It looks like a whole bunch of folks have got pending containers. Nothing's running yet. So what I might do, looks like my placeholders are not being shifted out. In the chat, can anybody shout if they've managed to get the notebooks open to this point where you can kind of see what we're running through here? Okay, somebody said it's still spinning with an empty build log. Okay, that's fine. Let me just change one little number here. So what I did is I pre-scaled my cluster with a bunch of placeholder containers that you should disrupt as you log in. It should launch a container for you, and that pushes out one of my like low priority containers that I put on to kind of save seats for everybody. But that didn't seem to have worked. So let me just make sure that's happened. Okay, lots of folks are now in like a running state. Few folks saying, okay, work this time. Yeah, so that seems to have cleared things up. There's this bit.ly link down in the bottom here of my screen share. Please head there if you haven't been able to get there yet. It should take you through to this notebook environment. The cluster may start trying to scale down now to numbers that we're at, but we'll see. Sorry, getting a little warm, just opening the door. So let me just keep an eye on the chat. How's everybody doing? Okay, folks are managing to get in. That's awesome. So once you're in, head to notebook number 2, and we'll carry on chugging through this together. So let's actually write some code. Let's dig into some code. I've been talking at you for 20 minutes already. Let's actually look at some interesting stuff. So let's start with a really minimal problem, and we'll start to like smush it into a way that can run on the GPU. So we'll start with a little bit of CPU code, and then we'll kind of squeeze it over onto the GPU. So we have to start thinking about our code in executing it in like a vectorized way, which if you've worked with NumPy, you probably feel familiar with. If you work pandas, that should feel familiar. If you've done anything with like a list comprehension, that is starting to feel a bit more kind of vectory. So if we have a look at this little piece of code here, if I have all the numbers from 0 to 10, and I have a little function called foo that just returns each one, doesn't do anything to it yet. It just returns that. If I want to run foo on each of those numbers in my range, I can do a list comprehension that looks like this. I can say foo I for I in data. And if I run this cell, it gives me a list with my numbers in, which is kind of what I would expect it to do. It's iterating through all of those things. But this is, this list comprehension is like a single call. I've said, here's a list of data, and here's a function. Please apply that function to my list of data. And I could write this as a for loop, but writing it in a list comprehension like this on one line is the right kind of mindset that we want for executing stuff on the GPU. So let's kind of move on and try and move this function in a direction that we can actually execute it on the GPU. So we return stuff. That's already a big no-no, right? We can't return stuff from our kernels running on the GPU. So let's change this cell around a bit. And we're going to say, let's generate our numbers again, 0 to 10. But instead of returning, we're going to have another array, and we're going to append our numbers to that array. So we're going to have this empty output array here. And when we call foo on our number, we're just going to append that to the list. And then if we do our kind of parallel execution here with our list comprehension, these numbers will all get added to that, appended to that output. And if we have a look at the output, it should look exactly the same. It's done kind of what we want. So our function now doesn't return, which is great. But there's a few other kind of little things we need to consider about our GPU. So we can't actually have zero length arrays like this and then add new elements to them on the GPU, sadly. We have to think about things in like a slightly more limited way. Sometimes writing code for the GPU, you feel a little bit like you got one arm tied behind your back because there are just a few things that are missing. Because it's kind of the compute environment is slightly less mature than the CPU environment. There's fewer kind of pleasantries about it. So one of the things is this output array needs to already be the length that we expect it to be, and we're going to update elements in it. Instead of adding new elements, we just say, well, our output is going to be 10 long, and we know that up front, right? We've got 10 numbers in our data, so our output is going to be 10 numbers long. So we need to kind of pre-initialize some array with 10 elements, and then our function is just going to go up and modify an element within that array. So we'll use NumPy just to simplify creating these arrays here, and also because NumPy plays nicely with number. So what we'll do is instead of doing our range, we're going to call numpy.asArray on our range. And that's just because it will be more useful when we do things on the GPU in a minute, having it as a NumPy array as opposed to like a native Python list. It's actually a generator here, an iterator. So anyway, in this example, we're now moving to NumPy arrays. If you've not used NumPy, kind of don't be too frightened at this point. NumPy arrays are, a bit like lists, but they can have multiple dimensions. They're a slightly lower level thing. They're implemented on the back end in C, and they're very fast. They're a nice way of working with arrays of data. So first thing we're going to create here is this 10 long array that's full of our numbers 0 through 9. Now we're going to create an output array. So this is just going to be, we're going to use mp.zeros, which is going to make us an empty array, basically. It's just going to be full of zeros. And we're going to specify it should be the same length as our data. So we make our data, and then we make it like an output that's the same shape and size, basically, which is 1 by 10, if you imagine it as like a two-dimensional object. Then we're going to modify our foo function again. So instead of appending, we're going to update an index, but we're going to update that index relative to the number that we get. And that makes sense in this context because we've got the unique numbers from 0 through 9. So we can access our array through the indexes 0 through 9. And we'll update the output array at those indexes. What we'll have to worry about in the future is our input data won't be like this. So we'll have to worry about how to get these indexes. But it turns out that's nice and easy on the GPU with number. So we'll go through this output array at each index, and we'll just set that index equal to I. So if I do this again with my nice little list comprehension, I haven't imported the NumPy. I forgot that cell. Now we can see our output array. This looks slightly different because this is what NumPy gives us as a repr, but we can see it's an array of numbers from 0 through 9. It's just showing us the decimal point, even though there's no thing. It's converted them all into floats for us, but it's done exactly the same thing. We've taken an input array, we've taken an output array, and we've called our function on each element and put the output of that function into our output array so we can work with it. Now, finally, the exciting time is let's do this, but on the GPU. So the first thing we're going to do is from number import CUDA, and we'll do the same with our data again, right? We'll have our 0 through 9, and we'll have our output array of zeros. And our foo looks slightly different here. We're not calling foo and passing it like an element from our input array. What we're doing is we're calling foo and we're passing it pointers to both of those arrays, the input and the output. So foo is kind of aware of both arrays at execution time. And this means that every single invocation of foo is the same, right? It's not being passed different data. It's not being handed anything. It's just, we're going to say, let's call this however many times we're going to call it. And you should just be able to see your data. So how does our function know what to operate on, right? Each function call is only going to operate on one number. So it needs to know which number do I work with. And one of the nice features about CUDA is, say we call our function 1,000 times, each of those functions can ask, which function am I? Am I function number 7? Am I function number 412? Like, it can ask through the CUDA API, who am I? Where am I? What should I be doing? And it will get back an index. So if we say we want to run it however many times, it can ask which index it is within that grid. So we can do here this call, CUDA.grid, and we pass it a 1 here just to say, we're working with one-dimensional grids at the moment. We'll get onto fancy multi-dimensional grids in a bit, but we say we're going to call this function 10 times because we've got 10 numbers in our array. We're just going to have the numbers not 1 through 10. If we're going to call it 100 times, we could either have the numbers like 0 through 10, or we could have like a 10 by 10 grid of indexes as well. But we'll come to that. We'll come to that. So we can get this I within our function. So now our function knows who it is, right? Each one gets a unique number, and it knows it can then do something different at this stage. And I think this is one of the things that like changed my perspective a little bit on GPU programming is, you know, where's the flexibility? If every thread has to do the same thing, what do I do here? And it's like, well, the invocation is the same. They both get passed a pointer to the array, but then they can ask, well, who am I? And then each thread can do whatever it wants, right? I can have if I equals 0, do this. If I equals 2, do this. And, you know, each thread can kind of go off on its different little path there. And so actually you've got all of these cores that you can get to do all of these different things if you want to. The only caveat here is when you call the function, everything blocks until every single thread is done. And if those threads need to talk to each other or do anything like that, you increase complexity. And if they, if one crashes or gets stuck or, anything happens, if something takes more time, all the rest are just going to wait for it. And so you're going to probably get loss of performance if you've just got one core like hanging around doing something that all the rest have already finished. So it's best to, you can have each thread do something slightly different, but it's best to have them doing things that are like roughly the same so that they take roughly the same amount of time to execute. And we're talking like nanosecond level of how long they take to execute here. So you just need to kind of keep everything lined up. But then we're going to do the same thing. We've got our output array here. We've got this pointer that we've passed in, and we're just going to update this element. We're going to say I, which is the number that CUDA.grid has given us, equals I. Now we actually want it to be the input array I. I think I've made a mistake there. I need to go and update that. But we want to set the output array I to be equal to the input array I. So it's just going to copy one number. And now we're going to do something that looks a lot like our list comprehension, but this is us actually invoking our kernel on the GPU. So we have our function that we've decorated with CUDA.jit. This is what turns it into a kernel. This is what stops it from being a Python function, turns it into a CUDA kernel, is this CUDA.jit decorator here. So we call our function kind of directly as if you would call any other function, but we're doing something slightly strange here. Instead of going straight to round brackets and passing it some arguments, we're giving it some square brackets first with some numbers in. And this is where we're specifying our like grid and our grid size, right? Our thread size and our block size. Now, the way that I've set this up just for this quick little example is we're going to have one block, and that block is going to be 10 elements long, which breaks all the rules that I said before. We're not really doing much clever calculating here, and it's not a multiple of 32, but we're just going to call this function exactly the number of times we need to call this function. So the number of times that foo will be called is these two numbers multiplied together. So 1 times 10, it's going to be called 10 times. And then we pass it our arguments through round brackets. So this function call looks slightly unusual, but hopefully makes sense as to what it's doing. It's kind of configuring the kernel with its number of invocations and then executing it kind of all in one go. So we can run this, and I don't know if you saw what happened, but my little GPU monitoring things on the side like flickered ever so slightly. And I've got a bit of memory usage now. That's mostly like my CUDA environment being initialized on the GPU. But I've got my array back, and this code here inside the function executed on my GPU. I ran some code, I wrote it in pure Python, and I ran that code on the GPU, and it worked. So hooray, if you're following along and you've run that cell, congratulations, you've run like a very basic function on a GPU floating out in the cloud somewhere. So that's great. There's a bunch of explanation here that I've kind of already gone through over what happened there. But now let's start pushing this a little bigger, because we only ran that function 10 times and we're meant to do it in multiples of 32. So we're like way below the smallest size we really should be running. And GPUs are kind of designed for having these functions called hundreds or thousands or millions of times, not 10 times. So let's have a look at maybe a slightly larger thing that we want to look at. So let's start with a big array. Let's have a random NumPy array that's got 30 million random numbers in it. And then let's make an output array that's got 30 million zeros in it. So we've got a nice big input, we've got a nice big output. And now let's actually do something. Instead of just like slotting a number from one into the other, let's do some maths. Let's not go crazy, but let's do some maths. So what we'll do is in our foo function here, let's do this on the CPU first and see how long it takes. This looks a bit like the example we were doing a minute ago. We've got a foo function, which takes I, and we're going to update the output array at I with the number from the input array at I times 2. We're just going to multiply all these numbers by 2, basically. And we're going to call that in a list comprehension. And now we've kind of moved our range isn't our input data anymore. So we've kind of had to smush that in here. So we're now going to call foo 30 million times. And each one of those invocations is going to update a single number in the array. It's going to take a number from the input, it's going to double it, and it's going to put it into the output. And it's just going to do that sequentially on the CPU in Python in probably the least efficient way I could think of writing this code. And if we run this cell now, one core of my processor is just going and grabbing a number, doubling it, and putting it into this output array. And it's not ideal. That took 15 seconds on this CPU. I think I wrote 10 in the notebook, so my local machine must be slightly faster than whatever this cloud CPU is. But it took 15 seconds to grab each of those numbers, double it, and put it into the output array. Now let's do exactly the same thing, but on the GPU. So let's just import math, because we're going to do a little bit of math in a second. But let's first off reset our output array. So we're just going to make our output a bunch of zeros again, so that we don't kind of cheat and look at the answers. But then we need to decide, well, how many times am I going to call this function? We know we want to call it 30 million times because there's 30 million things in the array. We've kind of decided that up front. That's something we know. But we have to specify this in a thread size and a block size. So let's just choose a thread size. The documentation said 128 is good, so let's go with 128. So what we need to do now is work out, well, if I'm going to do this in blocks of 128, how many blocks of 128 do I need? And well, we can work that out with this little line here that's just going to, divide the shape by the size of the thread, and then, give us the ceiling of that. So we're actually going to overshoot, because 30 million isn't divisible by 128. So we're going to call our function slightly more times, but those last threads that have kind of gone off the end of the array, in this case, they're actually going to fail, but that error gets swallowed up. But in the future, we might want to be a bit more thoughtful about saying, well, if you've gone off the edge of the array, you probably shouldn't do anything. We'll throw a little if statement in there, but we'll worry about that later. So we have our kernel again. This looks a bit like our kernel from before. We've cuda.jitted our function, and instead of passing it individual elements, we're passing it the full pointers to the arrays. They're grabbing their indexes from the CUDA grid, and then we're going to update the output array with the input array times 2. And then we can execute this. We can pass it our block size and our thread size, give it our 2 arrays, and call output. Let's see how long this takes. That took 293 milliseconds. And again, I don't know if the screen share quite captured it, but my GPU kind of fluttered ever so slightly. So that's insanely faster, right? The GPU took all of that data, it doubled all those numbers, and it handed them back again really, really fast, because it can run so many of these operations in parallel. So that's great. Now, if you've used NumPy before, you'll notice that my example here was mean, right? This was not a fair example. This is not how you would actually do this on a CPU. So comparing what the CPU here is doing with the GPU is probably not a fair comparison. But I did that on purpose because if we have a look at doing this in NumPy, which is like a C accelerated CPU way of doing this, it'll use all the cores in the CPU. It'll do the same kind of batch processing. And if I double these numbers and time it, actually, the CPU wins in this case. So although our GPU is crazily faster than doing it in pure Python, it's not as fast as doing this in C. And so let's dig a little bit into why the GPU wasn't faster in this case. Now, the answer to that is we're paying a memory transfer penalty. So we have our arrays of numbers, right? Our random array and our output array that we've created with NumPy. So those two arrays live on our CPU. But up here, we called this foo function, which is going to run on our GPU, and we passed it these two arrays. And the GPU has a whole separate set of RAM to our CPU. So numbers helping us out here, right? We've passed this kernel two CPU arrays, and number goes, oh, well, the GPU doesn't have access to those. So I'm going to copy those arrays onto the GPU. I'm going to call the function and it's going to work on them. And then you're probably going to want the answer back in Python CPU land. So I'm going to copy these arrays back again. And that's what's taking the bulk of this time, is doing this automatic memory management. Now, if we were doing something more complex in the function, then this memory transfer is going to be the same penalty each time. It's not going to get any longer to transfer that data. So if we do more work on the GPU, it becomes like a smaller and smaller slice at the moment. But right now, it's like dwarfing our calculation. And what if we did that and then called another kernel on our data and then called another kernel on our data? Numbers are going to be very happily and very nicely copy that data back and forth for us. And we're going to pay that penalty each time. So although having automatic memory management makes our life easier in our little hello world example, we might actually want to explicitly move our data to the GPU and explicitly move it back. But we have some functions that can do that for us. So we can do something like call CUDA.toDevice on an array to tell number, please actually copy this array to the device right now. We'll do something with it later. And we get this new pointer back, which is a pointer to the array on the GPU. And we can do the same with our zeros as well. And we'll kind of recreate those as we go here, just to make sure they are actually full of zeros. So I've run this cell. I've copied my random array to the GPU. I've copied my output array to the GPU. Now, if I run my GPU kernel on that array, it's not going to pay that penalty, right? The data's already there. It's already sat on my GPU. So if I run this, it's just going to do the doubling. And if I run this now, it takes 473 microseconds, right? Which is way faster than the CPU did it, So we've kind of cut down from 15 seconds doing it in like a, not very good pure Python way, gone down to, quarter of a second in a not very good GPU way, 1/10 of a second in a good CPU way, but now we're down to like thousandths of a second in a good GPU way. But the kind of challenge with this is our data is still on the GPU, right? It's still sat there. The output array is still on the GPU. We copied it there. It was already there. So number's not going to be helpful and move it back to us. So we have to explicitly say copy to host to pull our array back onto our CPU again. And we can have a look at the output here. So this makes a lot more sense if I want to run some code that's going to do a few different kernels, because I don't want to pay that penalty. If I do something like this, where I do foobar and baz on my data, I'm going to pay that penalty over and over. Whereas if I copy my data down, call foobar and baz, and then copy my data back, it's going to be much more performant. So that was kind of like an intro to number and how we can use number CUDA to run on the GPU. The next thing in this tutorial is number lab. So I'll go into the chat and answer any questions that are going on there. And yeah, so we'll see you back in 5 or 10 minutes. So there's a question here: what happens if two threads modify the same location in the output array? Well, you don't know which thread is going to get called first. If they're in the same block, then they might get called at exactly the same time. They might be like a few microseconds off. If they're in separate blocks, it might happen like a couple of nanoseconds later. Whoever's called second is going to win, right? That, you know, one of them is going to update the output array, then the other one's going to update the output array, and they're just going to kind of clobber each other and step on each other's toes. So you can do it. It's not going to be the end of the world, but you are going to kind of corrupt your data as you're writing. Another question. So I didn't understand how we've defined how many times the function is meant to be called. Okay, so those are the two numbers in the square brackets of what we've run, and how CUDA ensures that the order of input array is preserved in output array. Well, when we execute these functions, they're going to get unique indexes, right? From, you know, we called that 30 million times, so each one is going to get from 0 to 299,999,000, and each one is going to operate. You know, if you're thread 6, you're going to grab 6 from the input array and write to index 6 in the output array, so that the order is going to be preserved by using the same index. You could also do things like reverse the order in the same way that you know, that your function could write to 30 million minus the index, and it would like flip the order, and it wouldn't take any more time. It would just be you're kind of deciding how you're putting stuff back into memory. The next question is, how am I generating the GPU usage plots? So yeah, let me kind of jump back over here. I've had this open just to kind of show you what's going on, and we will get to this later. But if you click on this little GPU icon over on the left-hand side, there's a few little dashboards you can open. I've got GPU utilization and GPU memory open. You can kind of click and drag these around. Right? This is Jupyter Lab. You can kind of rearrange and scale and smush them about however you like. So yeah, if you want to open those up to see what's going on, then yeah, please do. But we'll come on to like how that works later. But this is like one of the big things that I've enjoyed working on at NVIDIA actually, is when you write code for the GPU, how do you know whether the GPU is busy and how much memory you're using? And you don't really have the same tools that you would do on the CPU. You can't do like top and free and those kind of Linux operations, or look at the task manager in the same way and get the same kind of output. So we've been working on a bunch of tooling to make it easier, and this is just with the Jupyter Lab integration. Oh, good, you found it. That's good. Is there any way to evaluate how long it would take to load the data onto the GPU? I mean, you can copy it and time it. All of these things are going to be down to how fast is your RAM, how fast is your CPU, what kind of PCI Express connection do you have from your CPU to your GPU? There's a whole bunch of factors in here. So the best thing to do is just time it and see. If I have to reuse the output for another operation on the GPU, I can copy the data back, so I can pipeline all the operations. Yeah, exactly. You can pipe them from one to the other with using the memory like that. Why do we need to copy the data back to the host? So you can see it, right? If the data is sat there on your GPU, I probably want to look at it. I probably want to use it in the input to some other function. I probably want to do something, you know, if there are other functions on the GPU, we'll leave it there. If there are other functions on the CPU, we'll copy it back. If I want to eventually do something like, you know, say this is happening as part of like a web server request, somebody's uploaded an image and you're writing some code that's going to detect whether there's a cat in the image. You want to copy the cat, you want to copy the photo to the GPU, ask if there's a cat. It gives you like a 1 or a 0. The output array is tiny, right? Is it a cat? Is it not a cat? And then you're going to need to answer that HTTP call. So you're going to have to copy that answer back to the CPU and then pass it to Tornado or, you know, whatever, to hand that back to the user. So, you know, you're used to working with stuff in CPU land. You probably want to copy stuff back to the CPU land. Can the copy to host method be used directly to instantiate an array on the GPU? Or do I need to first create an empty array? That's a great question. There are tools within Number for creating arrays directly on the GPU. You can also use CuPy to create arrays directly on the GPU. So no, you don't actually have to create the empty array like this. I just thought this was like an easier narrative to explain what's going on. Any book recommendations to learn more? It's a good question. I honestly don't know. Check out the Rapids blog. We blog about a lot of this stuff. We put a lot of it on developer.nvidia.com as well. We've started moving stuff there. I'm actually in the process of writing up a blog post series that is this tutorial as a blog post series that we're putting on developer.nvidia.com. I think if you find me on Slack, where I like said hello in the hello my name is room, I like linked to my NVIDIA blog profile in there. But yeah, no, I don't know of any books actually. Maybe we should write one. Do we need to copy to host our resultant data? So, for instance, plot it using matplotlib. Exactly. That's a great example of, if I want to calculate something, pulling it back to matplotlib. You've like preempted one of the next notebooks because we're going to do stuff with matplotlib and everything. But yes, matplotlib is a CPU-based plotting library, so we need to copy the data back to the host in order for matplotlib to plot it. We do have other tools, right? If you've used Datashader before, Datashader has like a GPU plotting backend. But yeah, that's one of the reasons why you would copy that around. So it's been 7 minutes. Hopefully you're kind of getting on well with this example. We're going to move on to the answers very shortly. I'm aware like this tutorial is like packed full of stuff. These questions are great. It's kind of helping me set the pace. I don't know whether we'll get up to the like more higher level stuff. I think it's maybe good to stick around this low level. But all these materials are available. They're all on GitHub. You can keep using them. I am going to have to shut down this binder at the end of the tutorial, I'm afraid, because it's eating up my GPU budget on the cloud. But yeah, you feel free to play with this stuff. You can run this notebook on any kind of Linux machine. Another question. How would we work with lazy data reading with the GPU/CUDA? Do you mean lazy data reading as in data that's, you might read part of the file or something to get the headers and then read chunks of it later? Yeah, I mean, that's going to be like a slightly higher level thing. And so these calls where we're copying stuff to the GPU is probably going to get wrapped up in that. Now, I know that's like a slightly fuzzy answer, but say you're doing some work, so I work a lot with Dask, right? I work on Dask and we do a whole bunch of lazy stuff in there. So if you're reading CSV files or something lazily, yeah, should we use a multiprocessing queue or Dask? Like Dask will handle some of this for you in that the higher level library, the CPU will probably peek in the file, right? If you're doing like to lazily load, you need to peek in the file and then you need to load the data out of the file when you actually want it. So in this case, the CPU would probably peek in the file to construct the like dummy object. And then when you actually need it, it would hand off to another library to actually do the loading and reading. This is like an active area that we're looking at the moment. A lot of this stuff is kind of shaken out for tabular data, so CSV, Parquet. But for array type data, we're still working on newer features. There's like an upcoming thing called GDS as well, which you might hear about in some of the gaming releases, but it's also available in the kind of work we're doing here in computation, where if you have an NVMe hard drive, so plugged into a PCI slot or plugged into like an NVMe slot, which is PCI really on the motherboard, the GPU can read directly from disk to GPU memory without having to go up through the CPU. Like the hardware is getting there. The software is like, we're still in the middle of working on it, right? But what I want to get to, I was literally doing some stuff yesterday where we're trying to read from hard drive straight onto the GPU to do some computation. That was with some like weather and climate data. Anyway, right, that's great. Thanks for the questions. I'm going to carry on like chugging through this material for a bit. Please do throw more questions in. I'll probably pause again in a minute and go back through. I hope that's kind of working okay for everyone. So let's go through the answers to this lab and see how you did. You can compare. So this challenge was to implement FizzBuzz, standard whiteboard programming question, but do it on the GPU for all numbers between 1 and 50 million. So let's import our dependencies first. Just make sure I'm going to try and tidy up my notebooks just because I don't want to run out of GPU memory or anything silly like that. So the first thing I'm going to do is make a big array of 50 million numbers because that's what we're going to do. Well, we want all the numbers from 1 to 50 million. So let's use np.arange to create all the numbers from 1 to 50 million. And then let's create an output array that will be the same shape and size. Now we need to calculate how many threads and blocks we need. Let's just use the chunk of code from the last one. So 128 is a good number. We'll use that and we'll calculate how many blocks we need. So we can, we can just have a look as well if we like, how many blocks do we actually need? If they're blocks for 128, we need 390,000 blocks to work our way all the way over this array. Great. So the next thing we need to do is write our kernel. Now there's some slightly frustrating features about running stuff on the GPU with number, and that's that string support on the GPU typically isn't as mature as integer or float support. So instead of having number, fizz, buzz, number, etc., they all need to be numbers, right? Our NumPy array is just going to be full of numbers. We can't mix types here. I tried to give a tip to head people off from going down the wrong path here. But what we're going to do is, instead of having our output array be, number, fizz, number, whatever, we're going to have our output array just be like 0 if it's not one of those, 1 if it's fizz, 2 if it's buzz, and 3 if it's fizz buzz. And then we can use our input and output arrays to kind of overlay that and convert back if we want to. So we'll call our function, it'll get input and output. We'll get the index for where you are in the array, in the grid. We'll grab the number out of the array. We'll do some if statements with some modulos to work out, am I fizz, am I buzz, am I fizz buzz? And we'll update our output array only if you are one of those things with the correct number. So if you're not one of those things, you just stay as a 0. So we can define that. And then if we run our data on the GPU, that was big. My GPU flashed all the way up to red then on my little utilization bar. And so if we look at the first 12 items from our fizz buzz, we can see it was 1, 2, fizz, buzz, 5, fizz, etc., right? And we can see it's calculated all of that for us, and it took half a second on 50 million numbers, which is fantastic. Now, the extra credit question here was to calculate the highest instance of fizz. We can use np.where here to work out. We can do np.where output is 1, so output is fizz, and then grab the 0th element, and which is just a result of np.where for some reason gives you a tuple of 1 item. So we'll grab that, and then we'll just do -1 to get the highest index. And so that's given us the index of the highest instance of fizz, not the highest instance of fizz. So we need to just select our index from data. So we can see our highest instance of fizz is 49,999,998. So hopefully some of you are able to get through that and work through that challenge. So let's move on to what I think are the kind of more compelling examples of what you can actually do with this stuff. I think what I'm going to do, given that we've got half an hour left, I'm going to aim to get through this notebook and hopefully up to the lab for this section, and then we'll stop maybe at section 3 and talk a little bit about how the dashboard is working, and then can leave the CuPy, CUDA, CUDF rapids type stuff for you to dig into in your own time if that's of interest to you. So let me just stop my other kernel as well. So we've been playing with numbers so far. That's all we've been doing, is just kind of prodding around with numbers, and let's do something a bit more interesting than that. So GPUs are very good at video rendering and games and all that kind of stuff. So let's do some image manipulation with our GPU, because it's very good at working with things that are in grids, and images are in grids. So let's import some stuff. Let's import matplotlib. We're going to use that for looking at our images. Let's grab NumPy and CUDA and all those kind of things again, and just configure matplotlib with the size. Now, the first thing we're going to do is, I've got a nice image that we want to have a look at. So I'm going to read it in with matplotlib. This is actually going to create as a NumPy array of our image, which is just really helpful since we're working in NumPy arrays already. So it's open this PNG file. This is just a regular PNG file that I found on the internet of the number logo. And I'm going to use matplotlib to read it in as a NumPy array. Now I can use matplotlib to also render it for us, to plot it. So if I call plot.show, we can see the number logo. So I have this array which has these pixel values of kind of all the colors and everything in this array. Now let's copy it onto the GPU so that we can do some work with it. So let's call CUDA.toDevice on our image, and then we're also going to grab like an output image, because we're going to do something to this image. We're going to manipulate it, so we need like an empty image to manipulate into. So let's make those two things on the GPU. We saw my GPU memory fill a little bit there as the array's copied down. But now this is where we need to start thinking about multi-dimensional indexing, because it's going to make our life a lot easier. So every time we've called CUDA.grid so far, we've passed it the number 1 to say, I want a 1-dimensional index. But our image here is 2 dimensions. Right? You can see it's 100 and something pixels by 400 and something pixels. So it would be really handy, instead of giving us, we're going to want to operate on each of these pixels, but instead of giving us like, index 732, which is probably, in the second row about here, it'd be great if it could just give us like an X and Y position as our index, because it is like an X and Y thing. So we can do exactly that. We can specify our threads and our blocks in multiple dimensions, and then we can ask for our index in multiple dimensions. So we're kind of, instead of, if you think about the function calls that we've done before, we've said, I'm going to run this function 50 million times. You can imagine each one of those functions like lined up in a row. You've got 50 million gone off over there. Whereas in this case, what we want to do is we want to kind of line them up in a square. Or each thread is going to represent a pixel in our image. Now, actually, our image is made up of multiple channels, right? We've got red, green, and blue, and we've got alpha as well, the transparency. So we want a three-dimensional image, a three-dimensional grid to represent our kind of technically three-dimensional image. It's a three-dimensional array anyway. We can check that by looking at the shape of our NumPy array. And it tells us, oh, it's 116 high, 434 pixels wide, and then there are it's 4 deep, and that just means there's 4 channels, red, green, blue, alpha. So what we're going to do is we're going to specify our thread size. And again, the same rule applies, right? We want 128 threads. We don't want to change that because it's a good default. So, but we need to specify 3 numbers because we want this to be a 3-dimensional index. So let's just specify 3 numbers that multiply together to make 128. Now I chose this like semi-arbitrarily in that I chose 4 for the last number because it's 4 deep. So we're not actually going to be like blocking over the depth, the channel depth of the image. Each block is going to cover the full like depth of the image, if that makes sense. And then I've just tried to make the ratio, the height and the width ratio roughly similar to the height and width ratio of the image, but that was just a choice. But now our calculation for how many blocks we need gets a little bit more complicated because we need to work out, well, how many blocks do we need vertically, how many blocks do we need horizontally, and how many blocks do we need deep? We already know that we only need 1 block deep, but let's still calculate it anyway, just for completeness. So we do our 3 calculations to work out how many blocks we need, and then it will give us like a 3 tuple of our shape of our blocks as well. So if I run these, I'll get my configuration settings for our shape. And if we multiply these together, I've just got a little list comprehension here that just multiplies these things together. It shows us that our grid of executions of our function is going to be 116 high, which is the same as our image. It's going to be 448 wide, which is wider than our image. And it's going to be 4 deep, which is the same as our image. So we need to be mindful of the fact that we're going to run more functions than we need, but it's just because we're working in these round numbers of the GPU. But let's worry about that as we write our kernel. So we're going to write a kernel to apply a Gaussian blur to our image. So we're going to check each pixel and we're going to blur it. And the way that we're going to blur it is we're going to look at a pixel and then we're going to look at all the pixels directly adjacent to it, and we're going to average them, and then we're going to update that pixel's position in the new image with the average of the little cluster. So the way we'll do this is we first need our indexes. So let's have X, Y, and C to represent X position, Y position, and channel. And we say CUDA.grid 3, can you please give me a 3-dimensional index? And because we've specified a 3-dimensional grid and block size, we'll get back the right indices here. But just bear in mind that X, I think I've actually named these wrong. They should be the other way around, but bear in mind that we are going to go off the edge of the image. So the next thing we do is have this if statement that says, if your indexes that you've been given by the grid are within the actual shape of the image, within the bounds of the image, then do this thing. And then there's no else, and then the function finishes. So all of those extra threads that are kind of hanging over the edge of the image, if you like, they're just going to not do anything. It's just going to be a no-op, basically. So all of those that are within the image, they're going to update the output pixel in the output array with the average of all of those surrounding pixels, right? So we've got our pixel in the middle, X, Y, C, and then, I've just kind of got a little grid of offsets here. I've tried to arrange the code in the layout of the thing to make it a little bit more visual. But you can see we're just going to add all of those together, then we'll divide by 9. That will give us the average of the pixel. So if we call that to create our function. We can now run our kernel. Now, this isn't like a very intense blur at all. So what I'm going to do is I'm actually going to run the blur a few times to make it blurrier. So I'm going to do a regular old Python 4i in range 5 to do 5 levels of blur. And all we're going to do is we're just going to call our kernel 5 times. So that's great in that we copied our data to the GPU, and now we're going to call our kernel 5 times. We're not going to pay the memory copy penalty or anything like that. So we'll get some nice kind of copying around going on. We're going to avoid the copying around. And then, but the thing we have to be mindful of is we've got our input image, and we're going to copy all the pixels into our output image. And then we need to swap them, right? The blur, like we're going to need to copy to somewhere, so we need to swap them over. So our blurry one ends up over here, and it's going to copy all of its pixels into our new output array, which actually is the original input array, but it doesn't matter. We're just going to overwrite it completely. But we're just going to flip those pointers each time. We're going to do that in Python. It's a very inexpensive operation. So we've moved our data to the GPU. We're going to blur it, flip the pointers, blur it again, flip the pointers, blur, blur, et cetera, et cetera. So if I do that, I didn't even put a time on the cell, but that ran very, very quickly. We ran over the whole image. We ran this blur. And now, if I want to actually have a look at my blurred image is still on the GPU right now, okay? So if I want to actually look at my blurry image, I need to copy it back to the CPU and then hand it to matplotlib for plotting. So we can do that all in one go, right? We can do GPU output, copy to host, and then call plot.imshow on there. And if we do that, we have a blurry number logo. Great. So that's great. We've actually done some kind of useful processing on like an array of data. And I hope this example is like a tangible thing. But then you can, we've done this to an image. You could apply this to video. You could apply this to gridded weather forecast data. You could apply this to, the output of like an MRI scan, or, whatever gridded data you're working with, you can do this kind of thing. You can apply it to tables of data. You can work with all sorts of things. You just get that kind of performance benefit of doing big chunked parallel operations. So the next thing here is another lab. Let me have a look at the time. We are nearly 10 past. This lab is pretty similar. So let's do 5 minutes for the lab. And then I'll kind of go over the lab. We'll talk a bit about inspecting what your GPU is doing, and we'll wrap up a bit. So please head to the lab, start working your way through that. I'm just gonna have a quick drink, and then I'll go over to the chat and answer any questions that have popped up over there. Okay, no, not a huge amount of questions, right? So since CUDA is C++ based, can we work with custom classes in JIT, or solely work with NumPy ND arrays? So yes and no. Number can only compile things that it is like aware of. So I think if you can make things which are based on Python primitives, but if you get too far away from that, you'll start running into issues. I mean, we've already kind of experienced that we've had to work around strings because strings aren't like super well supported. So you are going to run into some challenges there. It's best to work with as lower level Python primitives as possible, or work with NumPy arrays, or work with the number array, which we will actually maybe try and make time for in a second. So yeah, let's have a look. Another question: can you use the plus equals? I think so. I don't see why not. I think I was just writing it out the long way to be explicit. And then another question: isn't the last output GPU at this point? Just to be sure. That is a really good question, actually. No, it's not, because each time the name changes, right? So we're swapping the pointers, but every time we flip them, and then, oh yeah, no, you're absolutely right. My apologies. You're absolutely right. If I run this, it should be blurrier than the other one. Yes, thank you. It was a good spot. Yes, because we've done it 5 times. I might just change that to 6 times and save the notebook just for next time I run this, to make it a little clearer about what's going on. But oh no, that will still do it because we're still flipping the pointer. Yes, all right, I'll have a think about that. But yeah, you're absolutely right. Thanks for pointing that out. Okay, right, let's pop open this solution then, and we'll run through. So this is very similar to the one that we just went through. We start with our imports. We're going to read our same image in again with matplotlib. Let's have a quick look at it. Copy it down onto the GPU. We will work out our grid size. Now, we've gone from a three-dimensional need because we're blurring across all the dimensions. No, we're blurring each channel in each dimension. Whereas what we want to do in this one is we want to make our image black and white or grayscale. And so what we're going to do actually is just operate on a two-dimensional image. I know we've got our 4 deep, but each thread is going to need to access all 4 of those channels because we want to average the RGB, right, to make them all the same number and therefore gray. So instead of specifying a three-dimensional grid with 3-dimensional blocks with and a 3-dimensional grid, we're going to specify 2 dimensions. So we're still going with 128 threads. So we'll do 16 by 16. We only need to calculate the X and Y, and we'll set up our block shape as well. Now our kernel, again, looks very similar, but we're going to grab a 2-dimensional grid. So we'll get X and Y with a CUDA grid of two dimensions. We'll make sure that our thread is actually inside the image. And then in here, we're going to calculate the average of each pixel across the channels, right? So we want to average R, G, and B. And then we want to update each of R, G, and B with that average. And then we just want to pass the alpha channel straight through, right? If there's transparency, it should still be transparent. If it's not transparent, it should still not be transparent. So we'll just pass that number straight through. So we end up updating our output array. And then we can run with our same kind of call, right? Again, remember we have our function call with square brackets to configure it, how big it should be, and then our inputs. So if we run that, it runs on the GPU, and we can have a look. We have grayscaled our image. So in this first half of this tutorial, like this, this is a longer tutorial that we put in this 90-minute slot, but in this first chunk of this tutorial, we've really gone through about as low level as you can go in Python working on the GPU. We've written functions, we've executed those functions, we've moved memory around, we've done all that kind of stuff. But we've been helped throughout by these little plots on the side showing us how busy the GPU is and how much memory we're using and things. And that's all been thanks to this library that we have, which interacts with the NVIDIA driver called NVML. You can see we've got this. This is a screenshot from the GitHub page for this JupyterLab extension. You can see this is from a machine with 8 GPUs in, it's a server. And you can see all the kind of GPUs bouncing around, how much memory we're using. We're using Dask to record this as well. And so all of this is using NVML to query the GPU and say, how busy are you? How much memory are you using, etc. And we can do that ourselves if we want to kind of get into what the GPU is doing. So we can import PyNVML, this package. All of these packages, by the way, I didn't really mention. This is all in this binder environment. The Docker file for it is here. This is just based on the Rapids container, right, which has just got all of the tools in that we work with. But you can also install all this stuff, mostly with Conda, due to the complex dependencies, build dependencies. So if we import PyNVML, we first have to call NVML init, which just tells the library to connect to the GPU. But then we can do things like get device get count. It says, okay, in my cluster at the moment, I've got 1 GPU. On my workstation that I have for work, I have 2 GPUs. On the server, I might have 8. It'll tell me how many I have. I can also get the driver version. It tells me, this is driver version 450. And then I can also, I can ask specific things about each GPU. So we've only got 1, so it's not a huge thing, but we have to first get a handle for our GPU. This is kind of like a pointer to something we can ask about the GPU. So we're going to get the number of GPUs. We're going to do for I in range, how many GPUs we have, and grab a handle for that GPU. So I mean, this is just going to give me a list of one handle. But as I said, on other machines, it would give you more. And we can then do things like get device name for our GPU, for GPU in GPUs, right? We can go through all of our 1 GPUs and get the name. So this is a Tesla P100 PCI Express 16 gig model. This is, just the one that I picked in Google Cloud for my Kubernetes cluster. And I can do things like how much, get memory info, and then have a look at how much memory is being used. It is, half a gig, which kind of lines up with my plot over here. And then I can say how much is free. And it's like, well, this is a 16 gig GPU. So this is, it actually works out to like 17 or so with rounding. But yeah, this is how we can query these things. You can dig into this library. These are just direct bindings to the C library, so you have to dig through the NVIDIA docs. But yeah, this is kind of how these tools work, how you can integrate with other tooling if that's something that you work on or are interested in. But I just kind of wanted to share this. There's this extension called Jupyter Lab NV Dashboard, which integrates with Jupyter. It has also got like a standalone dashboard that you can look at these things. These are just like iframes in here. So I guess you could open these frames in new tabs as well and just have a look at these plots individually. So as well as being able to query what's going on in your GPU, let me come back up here. Let me just spend the last 10 minutes very quickly going through what else is in this tutorial. Please do feel free to save these notebooks and have a look through them in your own time. And also keep an eye out for the blog post series that I'm working on that is the full extent of this tutorial. But we have within the Rapid suite of tools, Cupizer was actually born out of the Chainer project, right? But we kind of we helped maintain it as part of Rapids as well. Is kind of like a direct replacement for NumPy that follows exactly the same API, but everything runs on the GPU. So you can kind of forget everything that I've just told you about threads and blocks and warps and kernels and all that kind of stuff. Because if you use NumPy and you want it to go faster on the GPU, you can just swap and use Cupi instead. Yeah, I'm going to spend a few minutes. Let's just have a quick look through this. I'll skip the lab, I guess. But if I import NumPy and if I import Cupi, I can make a CPU array, and I can also make a GPU array. These are just empty arrays full of ones. And it's very fast to make an empty array of ones directly on the GPU. I think one of the questions in the chat was about, can you make arrays directly on the GPU? Yes, you can. Cupi is a great tool for allowing you to do that. No, I'm having to call this synchronized call here just because some Cupi calls are like async. They run in a thread in the background. And so if I timed just this, it wouldn't have been true. So the synchronized is just making us wait for that to actually finish. We can see it's nice and fast to make empty arrays on the GPU. We can do basic operations, right? We can multiply all the numbers in the array by 5, and that is nice and fast on the GPU. We can do kind of more fancy multiplications that take longer and kind of see, wow, this is running 20 times faster on the GPU to do these multiplications. And we can also do kind of more complex operations. We could do like singular value decomposition from the linear algebra package. And again, running that on the CPU will take a few seconds. Running it on the GPU. This was being strange for me before, actually. Oh, there we go. I was taking about the same amount of time. Let's run it again. Yeah, okay. Something happens with initializing my GPU sometimes. But you see, this takes a lot less time to run on the GPU than on the CPU. So yeah, let's, and this last example here is just showing that one of the nice features about NumPy is if you ask NumPy to do something to an array that's not a NumPy array, but is NumPy-like, NumPy will dispatch to the correct library. So you can see we create our GPU array here with Cupi, but then we're going to call numpy.linearalgebra.svd and pass it our GPU array. And when we execute this function, NumPy will look at this and say, well, that's not a NumPy array. You should have called cupi.linearalgebra.svd, and it just calls that for you. So actually, if you want to swap a NumPy workload to being a Cupi workload, a lot of it is just changing the way that you create the data. You just import Cupi and create your data. Nothing else in your code base has to really change, and that will run the same. So there's a lab here. Let's skip over that. The last little thing I think that is probably worth mentioning about Cupi is all of these tools. We've talked about Number, we've talked about kind of low-level C++ stuff, we've talked about Cupi. All of these arrays, there's a cost to copying them around and transforming them and stuff. So one of the things that we have that we build as part of Rapids is something called the CUDA array interface. And this is an interface that allows us to just convert one array type to another. But but we leave the data alone, right? If we've got a big array of numbers on the GPU, that's a CuPy array, we can convert that CuPy array into like a number device array just by kind of swapping some pointers around and smushing some metadata about a bit, so that, but with leaving all the data alone, because it's just a C++ array on the GPU at the end of the day. All of these things have the same kind of primitive memory representation. It's just the like decorator on top, I guess, and the way it's exposed into Python. And so just to quickly show that, we can convert from one to the other really easily. If we create a big CuPy array and have a look at it, I might have just run out of memory. No, okay, that's fine. If we have a look at my big CuPy array, it's big. It's bigger than half my memory, I think. So I can't copy it in memory because it's taking up a lot of RAM, but I can convert it to a CuPy, a number array, just by doing toDevice on this, and it's not copied it. It's just given me a new array, and then I can do CuPy.asArray to convert it back again, and we just kind of smush the pointer around. Something to think about it a little bit to construct CuPy's representation. I think it also copied it back to the CPU just so we can see it again. But we can do this very easily, and a lot of libraries support this. So if you've got data in PyTorch, if you've got data in CuPy, you can kind of convert from one to the other type in a really straightforward way, which is something that was a hassle for a long time. So the last two parts of this, which I'm not going to go through, is we have a library called cuDF, which is exactly like pandas, but for GPU accelerated computing. So if you work with tabular data, if you work with pandas, have a look at cuDF. It feels the same, it looks the same, the API is the same. It's just on the GPU. And then we also have cuML, which is like scikit-learn. So there's a nice example here, if you do want to run through it, which loads in a data set on some people and whether or not they have diabetes, and then trains a model to predict based on inputs like blood pressure and glucose levels and things, whether or not that person has diabetes. And it does all the same kind of stuff. It uses cuDF and it uses cuML to load the data in from a CSV file to the GPU, train a model on it, and do some predictions. So that's kind of it. We're like roughly up to time. I'm going to save a
3
minute
minutes
to answer any more questions.
We have to give up the room. So if there's any last questions that Jacob could fit in just quickly there, and otherwise, if you could take it up with him on Slack, that would be amazing.
Yeah, exactly. Let me just have a quick look through the chat. Somebody asked, did the threads per block multiply to 256? Possibly, that might have just been a bug, but 256 is still fine. Can someone share the repo for the Number Lab notebooks? Yes, they are. I'll share it here again. So it's on GitHub. It's Jacob Tomlinson. I'll put this in the chat, right? That's probably the most sensible thing to do. So you can definitely go and find those notebooks. Yep. Oh, somebody else has put that in. Sorry, I should read ahead a little bit. How could someone create and work with temporary GPU arrays within a JIT function? Generally, you can't, right? Within a JIT function, you can't create new memory. You can only work with what you've been given. So you have to think about that ahead of time. Next question, does CuPy integrate with other packages the same way NumPy does? Yes, it does. It follows the same API, so things should just work. Is there any advantage of using NumPy plus NumberCuda instead of CuPy? If you want to get deeper and more gritty with the kind of functions you're writing, then yes. If you really have something where, we've done this kind of stuff with image manipulation, where we've written a custom kernel that calculates a blur on an image, there might just not be a standard function like that in CuPy for doing whatever you're trying to do. So yeah, if something is built into CuPy, great, go and use it. If you really need to get into the weeds, then use Number. And as I said, you can swap the arrays back and forth at any point to do that. We do it a bunch in Rapids for the higher level libraries. But yeah, that's it. It's 29 minutes past. We have to give up the room. Thank you all so much for coming. Thank you all for kind of sticking around. And we've had a good kind of solid number all the way through. So I really appreciate your attention. If you've got any questions, please feel free to ping me on Slack or on Twitter, and see you all around.
And thank you very much, Jacob. It was really informative, very detailed, and incredibly organized. So
sure thing.
Thanks all for joining. Bye now.